Today we're going to talk about the really interesting bit, which is game theory, bit of a tongue twister there. And I think this is basically what all of modern economics is about. And in particular, the way of thinking that game theory requires you to pick up is very different from how you might otherwise be inclined to think about problems. And it's actually very, very powerful and very helpful in sort of thinking through a lot of problems that you might face in the business world. Last time we wrapped up supply and demand and adverse selection, and this sort of is at least in spirit on complexity, a lot more similar to adverse selection than supply and demand, and it's like actually related in many, many ways. So we're going to talk about two different types of what are called games. One are static games, are played once and they're over and that's it, and dynamic or repeated games, which sort of reoccur, where players interact repeatedly. In a static game, players meet, they choose an action, and they get their payoffs, they leave, and they never play again. That's basically end of the world, kind of, that happens and then nothing else does. Certain examples of an advertising game where, two companies decide whether to run an ad campaign or not. Those would be the actions. They get their payoffs, think of profits, or since it's a static game, let's think about it as the present value of all profits that they make over their lifetime, and then they leave and that's it. And we're just using this sort of framework of game theory to think about how they might behave optimally. The actions generally, and you can soften those up, but in these types of games are generally unobservable. I cannot see whether you committed to running an ad campaign or not until we both sort of have taken our actions. They're simultaneous, so we decide at the same time. And they are one shot, so we're not repeating them. The last of which we're going to sort of think about a little differently as we're going along. The best response is just a term to say, I'm going to suppose you're going to take one of the actions you can take, and what is the best thing I can do given that you pick, say, action 1, whatever action 1 means. In Nash equilibrium, that's what we need best responses, basically means I am best responding to what you're doing, you're best responding to what I am doing. Doesn't mean that we're necessarily have to do these things, it's just helpful for us to identify what an equilibrium is that way. There are pure and mixed strategy equilibria. In this course, we're only going to talk about pure strategy equilibria, which means you're basically committing to playing action 1. In a mixed strategy equilibrium, you would be allowed to randomize over the actions you have, and then I would also, in turn, randomize over what I'm doing. There's two ways to solving these kinds of problems. The first one is preferred, as usual, I would say. Namely, by definition, a Nash equilibrium is where we're both mutually best responding to one another. So we're going to start by picking one of the player's actions, say player A. We're going to say, well, if player A plays action 1, and we're going to make this more concrete in a second when looking at an example, what is the best thing player B can do? Then that's the best response. Then we're going to say player A, if player A plays action 2, what is the best thing player B can do? And so on and so forth until we've covered all of player A's actions. And we're going to flip. We're going to say, well, let's start with player B's action. Say if player B plays action 1, what is the best thing player A can do? Then we're just going to try to find basically a combination of actions where both are the best response to one another. And that's just the definition of a Nash equilibrium. So as that, ad campaigns are sort of a standard canonical example here. In this one, we're going to talk about Delta and United, the two of the major airlines. I'm leaving out American here. And they were basically deciding whether to run an ad campaign or not. If neither of them runs an ad campaign, they both make $10 million. If Delta runs an ad campaign and United doesn't, they basically get 70% of the revenue that United would otherwise make. They're paying $4 million for the campaign. So it moves the payoffs in a way where it's like now United only gets 3, Delta gets 13. That's the top right corner. The first number, unless indicated otherwise, usually refers to whoever is the row player, so who picks the row, and the second one refers to the column player. Same as how you would index a matrix or an array if you're programmatically inclined. This game is symmetric, so it's the same for the case where United runs an ad campaign, Delta doesn't. And if both run an ad campaign, so their market shares don't change, but both of them pay $4 million, which is more of a dead weight loss. So ideally, if you want to look at sort of from a societal point of view, revenues or profits are maximized if neither runs an ad campaign, but we're going to see that this is not necessarily what's going to happen. So this is the payoff table. Now we're going to try to find the equilibrium. How do we do this? Well, we do it by trying to find best responses. That's the first approach we're going to learn about today. So we're going to say, well, if delta chooses no ads, what's the best thing United can do? If United also chooses no ads, they get 10. If they choose to run an ad campaign, they get 13. Running an ad campaign is the best response of United if delta decides not to run an ad campaign. I'm going to mark this by highlighting the 13 in bold green. Generally, if you have these tables, especially if they get bigger, it's really helpful to either circle in the numbers or highlight them with a highlighter or underline them, whatever you fancy, but this is generally how people go about marking whatever best responses are. If delta in turn decides to run an ad campaign, if United doesn't run an ad campaign, they get 3. If they do run an ad campaign, they get 6. Again, running an ad campaign is the best response. Now we're going to turn the thing around. We're going to say, well, if United doesn't run an ad campaign, what can delta do? Well, delta, when not running an ad campaign, gets 10. That's the second number here, right? And if they do run an ad campaign, they get 13. The best response is running an ad campaign. So we're going to highlight the 13. And now the same, if United doesn't run an ad campaign, they can choose between 3 and 6. So delta chooses to run an ad campaign, or that's the best response at least. And we have found all best responses. The Nash equilibrium now by definition is the cell where both numbers are highlighted. It does not necessarily have to be a Nash equilibrium. We can write games that don't have any of these types of Nash equilibria. But if they do, that's how you find them. So the optimal behavior of both airlines is running an ad campaign, even though they could both do better if neither ran an ad campaign. That's what's called a prisoner's dilemma. Since either one has a huge incentive to run an ad campaign conditional on the other player not running an ad campaign, they're going to end up in this terrible equilibrium down here where both of them run ad campaigns. We're going to see how we might be able to overcome this if we have a repeated game. In order to talk about the second type of solution algorithm, we're going to have to establish a notion that's called dominance. Usually when we think about a player having different actions, sometimes one of the actions is better or worse than the others. Here we saw for United, or delta, it was always better to run ads than not ads, right? In either case, irrespective of delta choosing no ads or ads, United is better off choosing ads. 13 is higher than 10, and 6 is higher than 3. That's what's called a dominant action. It dominates the dominated action. The dominated action is the one that's actually worse. And we're going to be specific when we say worse here. Worse means they give strictly lower payoffs in every single state of the world. Meaning, no matter what delta does, it's always better for United to run ads versus not ads. That's the definition of dominant action. We're going to be specific here and say we're going to talk about strict dominance, which means the payoffs are higher. Or, again, seeing it from the other side, the dominated actions payoffs are lower. Not equal, lower. That's important because otherwise we're going to run into other issues. We're not going to find all the equilibria out there. Now what we can use is called iterated deletion. We're basically going to start with one of the players, pick 2 of their actions, compare them, and if one is worse, we're going to say, well, the player is rational, meaning they're never going to play the bad action. They're never going to play whatever is dominated. So we're going to remove that action from the game as if it never existed. We can keep doing this, hence the iterated part of the definition, until we're basically left with whatever equilibrium there is. And as it happens, quite often actually, some actions might not be dominated initially, but once you have removed one of the player's actions, they become dominated. So you have to really check everything a couple of times to make sure that you haven't missed one of those. As such, we can use iterated deletion of strictly dominated strategies, or IDSDS, in order to find equilibria. That only works if the equilibrium is unique, if there's only one. If there are multiple equilibria, you're not going to find them that way, which is why the best responses approach is generally preferred. We are just going to start by eliminating the strategy from the game. We're going to try to find, sometimes you find it with player 1, sometimes with player 2, sometimes it doesn't matter. It's a bit of a brute force approach, especially in the beginning. And then we're going to remove all the strictly dominated actions. Do the same for the other player and repeat it until no dominated actions are left. And if the game has a unique Nash equilibrium, so 1, or unique pure strategy Nash equilibrium, I should say, it'll be whatever is left. we're going to start with this payoff table. Now, no real example. We don't need to think about what these numbers mean. It's just a game that we can solve. And now we're going to solve it using approach 1. So we're going to start again with firm B. If firm B chooses left, firm A, if they choose up, get 13, middle 4, down 1. So the best response is up. We're highlighting 13 here. If firm B chooses center, firm A basically has to pick between 1, 3, and 2. The best response is middle. And if firm B chooses right, the best response is down, since 8 is greater than 7 or 6. Now we're going to keep firm A's actions constant. We're going to say firm A chooses up. Firm B can pick between left, center, and right, which gives 3, 4, and 3 respectively. So center is the best response. We're highlighting the 4. Same for middle, where center is the best response. We're highlighting the 3. And if firm A chooses down, firm B's best response is left, since 9 is greater than 8 and negative 1. The Nash equilibrium here is middle center, as this is where the two best responses coincide. Now we're going to use approach 2. Now instead of holding one firm's action fixed and then comparing numbers along, say if we hold firm A's action fixed the row, we're going to compare numbers across rows. How do we do this? So here we're going to say, let's compare the payoffs of firm B, center and right. If firm B plays center, they get 4, 3, and 8 respectively. If they play right, they get 3, 2, and negative 1. 4 is greater than 3, 3 is greater than 2, 8 is greater than negative 1. So R is strictly dominated by C. So firm B is always better off playing C. What are they going to do? Well, they're going to play C, and we're going to remove R. We can keep this going. Firm A, let's compare M and D. If firm A plays M, they get 4 and 3. Remember, once we have removed R, we don't have to care about it anymore. If they play down, they get 1 and 2. They're always better off playing M. They're never going to play D. Let's remove D. Firm B, let's compare L and C now. L gives 3 and 1. C gives 4 and 3. 4 is greater than 3. 3 is greater than 1. They're never going to play L. And ultimately, comparing up and middle for firm A, if they play up, they get 1. If they play middle, they get 3. We can ignore all the other payoffs that they would get with these strategies. We've already established it. All the others are never going to be played. And here, clearly, up doesn't make sense. So they're going to play middle. And we find the same Nash equilibrium that we found using the alternative approach. If the Nash equilibrium is unique, both of them yield the same result. All right, now we're going to get into repeated games. As you saw, this game is basically, it happens once, and it's over, done, whatever. Now we're going to play the same game ad infinitum, so forever after. Think about it every day, or every year, or every month, whatever period suits you. And we're just going to keep doing this till the end of time. Now, what matters is no longer the individual payoff, but as you know from finance, the net present value of the payoff. And we're going to be given a discount rate to bring it to today, and then we're going to compare these things. Just as a brief reminder, the NPV formula, very important, is whatever you get today that you do not have to discount, so that's a P, plus starting next period, you also get P every period. You get, so the present value of that is P over R. So the important thing here is, and it's usually helpful to break it down this way, is you have P today, undiscounted, and just the present value of the perpetuity, the perpetual annuity cash flow that starts next period. That's something a lot of people seem to get wrong. P over R is just when the first payment is a year from now. So if you think about stocks and then you want to use Gordon growth formula, it basically says right after the dividend for this year has been paid, the stock price should value all future dividends. The first one occurs a year from now, at least with some stocks. I know some pay quarterly, we're going to ignore those. So, but like, since we're in game theory, usually think about what is my immediate gain from taking an action. So I get P today and the present value P over R over the future. And we're going to consider two strategy profiles. Now a strategy is no longer, I'm going to play up and you're going to play middle or whatever. Now a strategy is contingent on what's happened in the past and what's going to happen in the future. So for instance, I have to say, well, if you play this today, this is what I'm going to do for the next n periods. This is what I'm going to do till time runs out. And we're going to consider two types of strategies here. One is called trigger, basically, we're going to try to establish an equilibrium in which we both play nicely. And if one of us deviates, and we're going to see what that means in a second, we're going to punish that person. And how do we punish them? Well, we're going to play a really bad thing for the two of us until the end of time. That's what trigger strategy is called, or grim trigger strategy is really the harshest punishment possible. An alternative, in order to not be that harsh, is tit for tat. It basically means if you hurt me today by deviating, I'm going to hurt you tomorrow, and we're going to agree that you're going to endure it, and it's fine. But the day after, we return to cooperating. Sometimes that's enough to establish cooperation. The way I like to think about tit for tat here is like really, two children sitting in the sandbox, and one hits the other, is being hit back, and then they keep on playing. It's really this like immediate retaliation, but like not full out nuclear war till the end of time. And you're going to see why I'm using the example nuclear war is in a second. I did that before everything in Ukraine happened already. All right, so solving repeated games. The setup is fairly simple. You have usually players that play the same static game forever. So the game does not change, it's just what the players do over time changes. And most likely you're usually given a strategy. You're going to say, well, is the following in Nash equilibrium if we impose grim trigger, if we impose tit for tat. So the way we solve this is the concept is called one-shot deviation. We're going to say, let's say we're at any point in time, does it make sense for any of the two players to deviate today? If it doesn't help, like deviating today does not give them a higher net present value, they are never going to deviate since the game is repeating, right? If it doesn't make sense today, well, from tomorrow's point of view, we're in exactly the same situation since we're playing an infinite number of games. So if it doesn't make sense to deviate today, it's not going to make sense to deviate tomorrow or the day after, and that means that it's never going to make sense to deviate, and therefore it's optimal to play whatever the Nash equilibrium is. So we're going to compute the NPV under corporation. It's usually very simple. We have this corporation payoff C. You get C today and then an infinite series of C's. And then we have to compute the payoff when deviating. When deviating, we usually get a higher payoff today, D. That's usually greater than C. But then we're punished. So we get D today, and we're going to be punished by P tomorrow, and that we're going to discount by R, and that's our net present value. Tit for tat, it's a little trickier. It's easier to show it using an example. And then we're just going to compare the net present values, and we're going to say, well, whatever gives the higher net present value, or if corporation gives a higher net present value, I should say, then corporation can be sustained as a Nash equilibrium in the repeated game under the strategy profile that we're imposing. So the standard example here, and this is obviously worthy of a Nobel Prize almost, if you've watched A Beautiful Mind, you know where I'm going with that reference. A lot of this has been developed around mutually assured destruction during the Cold War. So one of the standard examples is that the US and the USSR are in Cold War and both have nuclear weapons. And they have to decide whether to take the nuclear option or not, whether to push the button and nuke the other country or not. And we're going to just impose that interest rates are 10%, and these are the payoffs annually. Think about them as what? I don't know. A trillion human beings alive. Think of them as dollar values. It does not matter. We don't need a notion for what these numbers really are. It's usually easier to think of them in dollar values, but it could really be anything that you can discount. So if both countries are in a peace state, then both get a payoff of 1. If one country can nuke the other, the country that gets nuked gets -1. The one that remains unnuked gets 2. And if both nuke each other, it's just 0 for both of them. The question we're going to answer is first, what's the equilibrium in a static game? And then if we go into a repeated game, can we sustain peace as an equilibrium either with trigger or tit for tat? So finding the static game, that should be easy, right? We're going to say, well, find best responses. If USSR picks peace, US can choose between peace and nuclear gives a higher payoff, so that's, in this case, the best response. Under nuclear, it's also the best response, so again, nuclear is dominant, peace is dominated. This is a it's called Prisoner's Dilemma, same type of game that we had in the beginning in terms of setup, just with different numbers, but comes out to be the same thing. And since the game is symmetric, so the payoffs are just mirrored, it works the same the other way around. So the Nash equilibrium really is the doomsday scenario where it's like, okay, we're going to nuke each other, and that's the best thing we can do. Not great. Now we're going to think about a repeated game, especially under trigger strategy. What we would like to sustain, that's the corporation payoff, which I'm going to call NPV co-op, is peace, peace. What is the payoff under peace? Well, we get 1 today, and 1 tomorrow, and 1 after the day after. So it's 1 plus 1 over 1 plus r, plus 1 over 1 plus r squared, plus, keeping the series going. And we know from the simple perpetuity formula that this is just 1 plus 1 over r. R is 10%, that was given on one of the prior slides. So the net present value of corporation is 11. What happens under deviation? This is a trigger strategy that we're going to look at today, or not today, but right now. The punishment under trigger strategy always is the static Nash equilibrium. You can argue why that is. It's not important for now. I'm going to skip that part. Key is just the punishment is going to be exactly this really terrible nuclear payoff. So if I deviate today, say I'm the US, instead of playing peace as we had agreed, I'm going to nuke the Soviet Union. I'm going to get 2 today. But the trigger strategy states that every period after that, we're going to be in the 0, 0 state. So we're going to get 0 tomorrow, 0 the day after, and so on and so forth. So we really only get 2 in net present value terms. So the conclusion is corporation can be sustained, and we all stay alive if we have this trigger strategy. And this is sort of the notion why mutually assured destruction works. You have nuclear weapons just to make sure that no one ever uses them. And this is a lot of how the Cold War played out. Now you're going to say, well, 11 and 2, there's a huge difference between the two. And especially, people are clumsy, and sometimes you press a button and you didn't want to. And is it really all that, like, if someone just accidentally presses a button and sends a nuke to a foreign country, or, a plane crashes that happen to carry in, like, we don't really want to be that harsh necessarily. So what we're going to look at next is the tit-for-tat strategy. Here again, we're going to say, well, under peace, we're going to get 1, 1 forever. Present value is 11. Now the deviation looks differently, though. If the US deviates and gets 2 today, we're going to agree that punishment is the exact flip of that. So if we nuke, or if the US nukes the Soviet Union in any given period, next period there's going to be a retaliation. But it's not going to be full-out war. It's just going to be, we agree that there's going to be retaliation, we're going to be nuked, it's fine, because after that, we're going to return to peace. I accidentally pressed a button, I was stupid, so I have to live with the consequences, so jumping to -1, but then we're going to be happy and cooperate again. Now the payoff is 2 today, right? If I deviate, I get 2 instead of 1. I'm going to lose 1 the day tomorrow, so -1 over 1 plus r. And then we're going to go back to corporation, so it's 1 over 1 plus r squared plus 1 over 1 plus r cubed, and so on. The net present value here is 2 for the deviation today, -1 over 1 plus r for being punished tomorrow. And then we're going to go back to corporation. That's the 1 over r that we had, but it happens 1 period later, so we have to discount by 1 period. And the present value here is 10.18 reoccurring. So now you can see the numbers are very close, but again, corporation is higher. So again, even when we're having this different kind of punishment, it is optimal to cooperate. Mind you, this is a symmetric game, as I said, right? So now by saying we check the US, and if the US, or like that's just like, if it's better for the US to cooperate than deviate, then that's enough, because the numbers are going to look exactly the same if we take the other side of the table and look at it from the Soviets' point of view. If you're given a game that's not symmetric, you have to check manually that it's also better for the USSR to cooperate than deviate. In the interest of brevity, I'm going to leave it at that here. But now you see sort of how these problems are solved. It's going to be variation of those, and usually you're going to see, sometimes it might say in a problem that well, we play trigger strategy, but instead of punishing forever, we're just going to agree to punish for 4 periods. Does that work? Or it's going to say, we're going to play tit for tat, but we're going to go back and forth twice. It's all variations of this. If you're comfortable with the formulas and how you compute NPVs, it should be very easy. As I said, this is basically the entire rationale behind MAD, or mutually assured destruction. Now, sort of like totally different topic. Now we're going to look at auction design. Auctions are, simply put, mechanisms to allocate a good between many potential buyers. There are different types. You can do it with an open outcry, a sealed bid. Sealed bid is a little more like eBay, I would argue. Open outcry is what we see a lot in, at Sotheby's and where you can just basically shout or raise your hand in order to bid, so everyone knows whatever the bid is. The valuations, so valuation usually refers to the willingness to pay. Now but differs obviously between individuals. Can be either private value or common value. Private value auctions, eBay or a painting at one of the fancy auction houses. Common value is, we usually think about this as, and you saw that in the lecture, an oil field. Oil fields are often assigned by auction, and usually every individual playing or bidding has the same value for a barrel of oil, namely whatever the market price is. Sealed bid auctions are auctions in which the bid is submitted in secret and the price is determined with one of a couple of pricing rules. Usually what we think about in terms of auctions is the first price, so the highest bid wins. That is not what eBay does, and there's a reason for that. A lot more common, and obviously for us a lot more helpful actually as economists, is the second price auction, where the winner pays the second highest bid. If you think about how eBay works, the way eBay works is everyone puts in their bid, but the current bid, and also what's ultimately going to be paid, is just the minimum, it's usually $1 or whatever the difference between bids has to be, over the second highest bid, right? And then eBay increases that price as other bids come in. If yours still is the highest, sort of creeps up on whatever your highest willingness to pay is. There's a reason for why it works this way, and it's actually going to make a lot of sense economically because it makes problems a lot easier to solve. Lastly, there is what's called an all-pay auction. This is often what you see in charity when basically everyone pays their bid. There is an equivalence theorem that says if designed correctly, all auctions give you the same payoff. That's why we can easily just look at one of them, and we're going to look at the second price auction. In addition to sealed bid, there's open outcry. So everyone basically shouts their bids, and then the item goes to the highest bidder. That can be in ascending or descending order. The standard example for ascending is the natural one, right? It's like whatever you see when you try to look at what auction houses do, or when you look in the movies, it's always ascending. Descending is used to be common in the Netherlands, flower auctions, where you start from a high price and the price is lowered until someone says, well, I'm going to buy it at that price. Again, doesn't really matter for us here, more of a sort of filling in the background. The other differentiation I made was private versus common value. In the private value auction, all bidders have different valuations. So if we're all bidding on a painting, one of you might be willing to pay $5 million. I'm just willing to pay $5. We all have different private valuations or willingness to pay for it. And this is usually due to different preferences. Common value auctions, as I said, oil fields, for instance, basically everyone values the object the same way, but we're not sure about that value. Oil field, think about, well, we all know that a barrel, I have no clue what it currently goes for, even though I am invested in commodity ETFs. But I know they're doing well, at least for a time being. But the object has an uncertain value because we don't know how much oil there is in the ground. So the different willingness to pay of bidders is just due to differences in information about the value. You might think there is 5 million barrels, I think there is 4, and that leads to the difference in our valuations. The winner's curse, sort of thinking that if you win the auction, you've overbid. that is it's the most common phenomenon in common value auctions, where if you think about sort of how much oil there is in the ground is somewhat normally distributed, the winner is the extreme, then probably the actual value is somewhere in the middle, and by winning they know that they had a much more positive view, or they were overconfident in terms of how much oil there would be in the ground. As a quick aside is that we're going to look at second price auctions. Why is that? In a second price auction, it's dominant, and we talked about what dominance means, to bid your willingness to pay. Why? Well, if you bid more than your willingness to pay, you either win and you pay whatever the second highest bid is. It's not so bad, but it can happen that you have to pay something that's higher than your willingness to pay. You don't want to do that. That's bad. Negative value. We never do that. If you bid below the willingness to pay, that just reduces your probability of winning, because you're always going to pay the second highest bid. So if you bid exactly your willingness to pay, or you bid the highest that you're willing to pay, then it maximizes the odds of you winning and not while avoiding the paying more than your willingness to pay. So if you bid exactly your willingness to pay, you either win and pay something that's weakly lower than your willingness to pay, right? Because you're paying the second highest bid. So if you're the highest bidder, you're paying whatever the next highest number is. So you likely get some positive value, or you lose and get nothing. And this clearly is the best thing you can do here. You can show this more formally, but it gets really annoying really fast. So we're going to leave it at that. You can always take it as a given. If you're told it's a second price auction and you have to figure out the equilibrium, it's always going to be everyone's bidding their willingness to pay. So bids don't depend on the information on the valuation of others. That's important. I'm going to bid my willingness to pay. I don't care about anyone else's willingness to pay. In a first price auction, that's different. In a first price auction, I know I'm going to pay what the highest bid is. But I have an incentive to bid a little lower than my willingness to pay in order to get some positive value in case I win. But by how much I what's called shade my bid, by how much I go under my willingness to pay, depends on what I think your willingness to pay is. But your bid is going to depend, or what I think your bid is, and that's going to depend on what you think my bid is going to be. So it's like the circular argument that's really hard to solve. So that's why we're just going to leave that aside. First price auctions suck, but there's this awesome auction revenue equivalence theorem that says the revenue of the auction is the same. So it doesn't matter whether we're going to look at a first price or second price auction, the revenue from the auctioneer's perspective is going to be identical. So that's why we really, really like second price auctions. They make our life nice and simple, and that's what we're going to stick with throughout the course. The setup for auction problems is usually very standard and simple. You have multiple bidders. They're usually given some weird set of names. There's some uncertainty regarding the value of the object. Usually the way we phrase it is a bidder has either a high or low valuation with different probabilities. And then to solve this, we're going to just apply a very simple and straightforward solution algorithm. We're going to compute all different combinations of willingness to pay for the different bidders. We're going to compute the probability of each case, and then we're just going to compute the sales price. And ultimately, that gives us revenues and expectation, and that's how we solve every single problem that looks like an auction. Here we're going to consider a second price auction of a single item. There are only two bidders. Each of them have a private valuation of either 100 or 300, and they're independent. So it could be that both of them valued at 100, that one of them values at 100, the other one at 300, or both at 300. And the probability of these cases is always half times half. Since it's equal probabilities and independent, we can just multiply the two. And if there is a tie for the highest bid, the winner is selected at random. That doesn't matter much. So what is the expected revenue from the auction? And now we're going to suppose that there is a third bidder, and there are obviously three, and all of them either have a valuation of 100 or 300. And then we're just going to look at how this changes things. All right, so we're going to start looking into the first question. As I said, we're going to compute different cases. And specifically, we want to know what kind of willingness to pay combinations we have. I already said there's going to be 4 cases in this setting. Namely, we can have that the willingness to pay of A is 100 and of B is also 100. We can have 100 and 300. We can have 300 and 100, or both of them valuing it at 300. Now, what is the bid? And this is where the beauty of the second price auction comes in. Well, everyone's just going to bid their willingness to pay, so we can just basically copy everything over. So now, what is the probability? I'm going to call it prob A, prob B. So what's the probability that A is going to have a willingness to pay of 100? Well, that's 50%. Same for B, and then actually same for all of them. We established that. So the actual probability, I'm going to call it P here, is just the product between the two. Since they're independent, we can do it that way. What have I done here? Well, I'm just going to say the first case, which is going to happen 1 out of 4 times, A is going to have a willingness to pay of 100, so does B. They're both going to bid 100. Now all we need is the winning bid. I'm going to call it bid W. Bid W is just the second highest. What was the? Bid W is just the second highest of the two bids. Since they're the same here, the second highest is 100. 100 is smaller than 300, so the second highest is 100. Same here, and here the highest, the second highest is 300, right? It's a second price auction. I shouldn't call it bid W. I should really call it the price at which it's going to be sold, P sale. So now what do we do? Well, we're just going to compute to get the expected revenue. We're just going to compute the sum product between the probabilities and the sales prices. This just means 25% times 100 plus 25% times 100 plus 25% times 100 plus 25% times 300. That's what this formula does. We can show this more clearly if we just multiply these through. Basically, we're taking the expected value over this P sale column, right? And that's the revenue the auctioneer is going to make. All right, now we're going to basically keep all of this, but we're going to play around with it a bit more. Now, what we're going to add is a third bidder. Let me make room for that person. So there are now 3 bidders, each of which have the private value of 100 or 300, again, equal and independent probabilities. How does it change things? We're going to get 2 more cases, right? We're going to have willingness to pay of C. And now we can have cases in which everyone is willing to pay 100. We're going to have cases in which willingness to pay of A and B is 100, willingness to pay of C is 300. We can have 100, 300, 100, 300, 100, 100. Oh, sorry, it's actually 8 cases that we can have now. 100, 100, 100, 100, 300, 100 now. All right, 100, 300, 300, 300, 100, 300, 300, 300, 100, and everyone can have 300. The same logic as to what the bid of C is going to be still applies. This is always going to be the willingness to pay. Probabilities are still equal between all of them. So this is the probability of C having their respective willingness to pay. The total probability now is the product of the 3. So it's just this times that. And the sales price is always going to be the second highest bid. In the first case, when everyone's bidding 100, that's 100. In the second case, where we have 100, 100, 300, it's still 100. In the third case, it's 100. In the fourth case, 300, 100, 100, it's still 100. 300, 300, 100 means that the second highest bid now is 300. 300, 100, 300, same, same, same. And now, if we want the expected value, we're going to, again, do the sum product between the probabilities and the prices. And now the expected revenue is $200. Now, the question is, why does the additional bidder affect the outcome? It's actually quite simple. If the additional bidder happens to have the willingness to pay of 100, it does not affect the sales price, right? Because it's not going to increase the price. However, in the cases where now two individuals have a willingness to pay of 300, the second highest bid, and this is a second price auction after all, is no longer 100 but 300, and thus elevates the expected revenue. The more bidders there are when they're identical like this, the higher the revenue is going to be, because it just increases the number of cases in which, or the relative share of cases in which the second highest bid is going to be 300. What's important here, no one bids their expected willingness to pay. On the day they show up to the auction, they're either going to have a high or a low willingness to pay. They're going to bid that. They're not going to bid whatever the expected value is. That's really, really crucial, and that's what a lot of people are going to draw. Okay, I hope this one is going to help you in solving the next problem set. And next time we're going to talk about agency and incentives, basically the last topic of the course. Let's see how that's going to go. See you then.